Okay. Hello, and thank you for joining our webinar today, sponsored by the Access Forum. It is a great pleasure for me to welcome Charles Manski, who will present his paper, Minimax-Regret, Climate Policy with Deep Uncertainty in Climate Modeling and Intergenerational Discounting. It's a paper he co-authored with Stephen Tacanio and Alan Sandstad. Chuck has been Board of Trustees Professor in Economics at Northwestern University since 1997. He previously was a faculty member at the University of Wisconsin-Madison, the Hebrew University of Jerusalem, and Carnegie Mellon University. He received his BS and PhD in economics from MIT, and he has also received honorary doctorates from the University of Rome, Tor Vergata, and the Hebrew University of Jerusalem. Chuck's research spans econometrics, judgment and decision, and analysis of public policy. He is author of multiple books, and just to name two of his most recent ones, in 2019, he published Patient Care Under Uncertainty, and in 2013, he published Public Policy in an Uncertain World. He has served as director of the Institute for Research on Poverty, chair of the board of overseers of the panel study of income dynamics, and chair of the National Research Council Committee on Data and Research for Policy on Illegal Drugs. Editorial service includes terms as editor of the Journal of Human Resources, co-editor of the Econometric Society monograph series, member of the editorial board of the Annual Review of Economics, and member of the Report Review Committee of the National Research Council. Chuck is an elected member of the National Academy of Sciences. He is also an elected fellow of the American Academy of Arts and Sciences, the Econometric Society, the American Statistical Association, and the American Association for the Advancement of Science. He's also a distinguished fellow of the American Economic Association and corresponding fellow of the British Academy. But before I pass the floor to Chuck, I would like to give you some background about our webinar series. Today's webinar is a second of our series on modeling frameworks for climate change mitigation policies. The first webinar was on March 23rd, and the speaker was Mike Barnett from the Arizona State University, who presented his paper, Climate Change Uncertainty Spillover in the Macroeconomy. It's a paper he had co-authored with Lars Hansen and William Brock. In their model, the policymaker was faced with uncertainty related not only to carbon and temperature dynamics, but also uncertainty about the curvature of economic damage functions. Furthermore, policy outcomes included endogenous feedbacks and dynamic impacts on the social cost of carbon. They argued that a single discount rate was not appropriate for the level of ambiguity of their model, and instead, they borrowed the idea from asset pricing of representing uncertainty adjustments as a change in probability over future macroeconomic outcomes. So since we are on the subject of discounting, I would like to invite you to answer the short survey that follows. So to the first question, what should the discount rate be for future climate-related monetary damages under deep uncertainty? 53%, 50% answered it should be relatively low, between 1 to 3%. 35% answered it should be high, between 5 to 7%. To the second question, policymakers should set the discount rate for future climate changes to reflect pure rate of time preference. No one voted for this one. Intergeneration inequality aversion was voted by 25%. All of the above was voted by 70%. So, Chuck, the floor is yours.
It's an interesting, thank you, Anastasia. It's a very interesting device to have this survey question. As we begin, we will be talking about the discount rate quite a bit today. So I'm going to go to share screen in a moment. Before I do that, I think if you see on screen the same as I do, you see Steve DeCanio, who's my co-author, who's on. Third co-author, Alan Sanstead, he had an appointment. He's out on the West Coast in Berkeley. He has an appointment, or I hope he's going to be able to join us early, but later, but I'm not sure. So I'm going to try to share screen right now, and I hope you can see it as I do, and then we will begin. Now, I understand we have about 40 minutes to talk. This is a technical paper underneath, and clearly in 40 minutes, one can't get into all of the technical work, and some of it in particular may be unfamiliar to you, the type of modeling that we're doing, but I want to get somewhat into it. So the first half, I'm going to be totally verbal, and then go through the, at least in the extent that I can, the type of modeling we're doing. I know that there'll come a point where we get into the details of the modeling where I'll just have to skim through or go right to the conclusion. We'll see how that goes. Okay. So to begin, I think everyone probably is well aware of what integrated assessment models are, which have been used by economists and climate scientists to quantitatively evaluate the benefits and costs of alternative climate policies. The typical setup is, follows a general utilitarian practice in welfare economics of considering a social planner who wants to make optimal trade-offs. And in this particular case, the trade-off is between the cost of carbon abatement and the damages from climate change. In the literature, the planning problem has typically been formalized as an optimal control problem with three components. The first is the physical science component. There are equations that couple greenhouse gas emissions and abatement to the accumulation of greenhouse gases in the atmosphere and resulting temperature increases. So we economists borrow the physical science from the climate science literature. The economic parts are under 2 and 3. First, there's a damage function that quantifies the economic effects of climate changes usually in terms of loss of global GDP as a function of temperature increases. So that's the damage from temperature increase. And then, of course, there's a cost of abatement that expresses the cost of actions to reduce emissions relative to some stipulated baseline emissions trajectory. The cost and damages are typically expressed as percentage reductions in gross world product. The problem is to minimize the cost of abatement and damages over a time horizon. And you can write down this control problem. To solve it presumes that the planner knows enough to make optimization feasible. However, there are a whole set of uncertainties, both on the physical science side and the economic side, and that's what we're doing. And also the earlier paper that Anastasia mentioned a couple of months ago, I was also on uncertainties, but coming at it in a different way. On the physical science side, I'm going to go over this in broad terms now and come back to it in more detail a little bit later. Physical scientists do what they call multi-model ensemble analysis. They don't know the right climate model. There is no consensus physical science climate model. There are multiple models in the literature. To cope with uncertainty about what the correct model is, that's what they call structural uncertainty, they typically get predictions of future climate from multiple models, and they take averages of the outputs, either simple or weighted averages, and I'll say more about that later. Now, economists don't know the correct damage function or abatement function, so we have our own uncertainties there. Interesting distinction is that in the economics literature, there, as far as we're aware, there is no typical practice of combining multiple functions by averaging forecasts. Rather, different studies report different findings. There's no attempt to combine them through an averaging. Now, Alan Sandstedt and Steve DeCanio and I wrote a first paper that was published just a little more than a year ago in the Proceedings of the National Academy of Sciences, where our focus was on the structural uncertainty in the physical science climate modeling. And we did that as a problem of partial identification generating deep uncertainty. If you're familiar with econometrics, then you may know what partial identification is. Deep uncertainty is the term that the physical scientists use. You could also use the word ambiguity, meaning the same thing. Or if, I know that if there are central bankers on with macro background, then you would know this is Knightian uncertainty. They all mean the same thing. The problem, whatever you call it, refers to situations in which the underlying mechanisms, dynamics, or laws governing a system are not completely known. And the problem is not the textbook statistics problem of having a small sample. If it were a statistics problem, then the uncertainty would disappear as sample size increases. But identification problems are the problems that do not go away as sample size goes up. So even if you collect lots and lots of data, big data, if you will, from a given sampling process, you're not going to be able to separate to determine what's the right physical science model. And I might say again, for those who are, I'm not a macroeconomist by background. My applied work until this has almost always been micro work. But if you are a macroeconomist, then you know that there's no consensus on the right macroeconomic model. And that's similar to the lack of consensus in physical science on the correct climate model. And it's not simply a question of statistical imprecision, it's a question of identification. So the question then is, how are you going to deal with these this uncertainty? And we use the Minimax-Regret decision criterion, which I will try to explain in as much depth as I can later on, to account for deep climate uncertainty in integrated assessment models. So we have a theoretical framework for cost-benefit analysis of climate policy based on Minimax-Regret, and then we apply it computationally with a relatively simple, but still computationally challenging, I must say, integrated assessment model, and we produce, real results from that. Now, the early work, the first paper that Steve and Alan and I did focused on the climate science uncertainties, but of course there are many uncertainties on the economic side. But we had a choice to make in writing this paper as to which of the economic uncertainties we wanted to focus on. Anastasia said that in the earlier paper that you heard, the focus was on the uncertainty in the damage function. We do a little bit on that by doing some sensitivity analysis on the damage function, but that's not our focus in this paper. Our focus is on uncertainty about what discount rate to use. It seemed to Stephen Allen and myself that this really has been the most contentious issue in the economics literature as to how to assess the cost and benefits of policies across generations. And what that means quantitatively is what discount rate to use in setting up the dynamic optimization problem. And what we do is we study choice of climate policy that minimizes maximum regret with deep uncertainty, jointly regarding both the correct climate model and the appropriate discount rate to use, which is the embodiment of intergenerational assessment. Now, I think everybody knows, anyone who's any economics background at all, even undergraduate, knows about looking forward-looking assessment of policies or private decision making. We are, for a long, long time, we use discounting. In public policy, the question of what discount rate to use has always been controversial. And it matters. I mean, this is, economists have always been very sensitive to this. It particularly matters with climate policy because the time horizon is so long. And what shows up very easily is that if you use low discount rates, that's going to favor policies that reduce greenhouse gas emissions aggressively and rapidly. High rates are going to favor policies that act modestly and slowly. Qualitatively, the reason for this is very simple, is that the real damages from global warming come not today or tomorrow, but maybe 100, 200 more years in the future. And so it's a question of how much do you care about the future, and the deep discount rate is what embodies that in the economic models. So what we do, and this is where we really take a leap and move away from the mainstream in climate economics, is we do not use any particular discount rate. Instead, we suppose that the appropriate discount rate lies within an interval. The particular interval that we're going to use for our computational work is 1 to 7%, which is what was used on that survey you were doing. And that's all you know, is that the discount rate should be somewhere between 1 and 7%, but we're not going to try to pin it down. And also, we're not being Bayesian about this. Some of you may think, well, if you don't know what the discount rate is, put a subjective probability distribution on it. No, but that's not what we're doing. We're not going to put a distribution on the discount rate. We're just going to say the discount rate lies between 1 and 7%, and that's intrinsic uncertainty that we have to take account of in decision making. You may wonder, how do we do that? That's what Minimax-Regret does, and I'll explain later. But the mathematics actually, I won't say it's easy, but it's a straightforward generalization of the earlier work that we did. The MSD stands for Manski, Sanstedt-Decanio, which was the earlier paper we did. There, we focused on uncertainty on the climate model, and we said that we took 6 prominent models in the climate science literature, and we said we don't know which one's correct. And instead of averaging the results from the 6 prominent models, we say, well, one of those 6 is correct, but we don't know which. Of course, it may be that none of them is correct, but we did make the assumption that one of those 6 models is correct. It's just that we don't know which. But in that work, we assumed that the correct economic model is known. Okay, so going back to what we did then, this is the simpler version of what I'm going to talk about today. We suppose that a planner compares 6 policies, each of which chooses an emission abatement path that would be optimal if one of those 6 climate models were correct. Because if you knew the correct climate model, then you'd have an ordinary dynamic optimization problem, and you could solve the optimal control problem. So, but we don't know which one is correct. So what's regret? If you're not familiar with the term regret, literature on this goes back to 1950 or so. I've been writing on using maximum regret as a way of evaluation of public policy under deep uncertainty for close to 20 years now. There's a fairly large econometric literature on this by now, but if you're not familiar with it, regret is the loss in welfare if the model used in policy making is not correct, and consequently, the chosen abatement path is actually suboptimal. So what regret measures quantitatively is the degree of suboptimality, the loss relative to that you suffer relative to the what would be the optimal policy if you were to know the true state of nature. Well, you don't know what the true state of nature is, the true climate model is, so you can't minimize regret, which is what you would like to do. But what you can do is calculate maximum regret across all possible models, or in decision theory language, across all states of nature, and you can choose a policy that minimizes maximum regret. Or get away from the technical language, it minimizes the largest degree of suboptimality across all 6 climate models. So that's what we did earlier in the PNAS paper. Now, the new paper, mathematically, as I said, is very simply an extension of that. It says that, well, we still have the uncertainty about the climate model, but now, in addition, we have uncertainty about the discount rate. And so we say, well, the discount rate it could be 1%, 2%, up to 7%. It could, of course, be the entire continuous interval, but as we discretize it for simplicity and say the discount rate to be used is just 1%, 2, 3, 4, up to 7%. Now, what are we doing when we say that the discount rate is uncertain? There are multiple reasons, and I'll introduce this now and then talk more about it in just a bit. There may be an empirical uncertainty about the future of the economy, which shows up as one of the determinants of the discount rate. But the part where we really deviate from standard climate economics is that there may be normative uncertainty, or even more different from the normal climate economics literature. There may actually be disagreement about how the current population does or should value the welfare of future generations. Okay, now I'll talk, as I say, I'll talk more about that later. But given that we do that, given that we have joint uncertainty about the climate model and the discount rate, we suppose that the planner compares 43 different policies. Well, there are 6 possible climate models, and we have 7 possible discount rates. You multiply 6 by 7, and that gives you 42. If you want to optimize under each of these settings, that gives 42 possibilities for policy. The 43rd is a passive policy in which there's no abatement at all if you just follow the baseline. And of course, the Minimax-Regret, as before, it just minimizes maximum regret across all these policies. Now, the bottom line that we'll come to after doing all the technical work, and this goes back to that first survey question that Anastasia posed, it's going to point to use of a discount rate of 2% for climate policy. So that we're not saying this exogenously, we're saying that the solution to the Minimax-Regret problem is to act as if 2% is the discount rate. That doesn't say that, that doesn't solve the problem of uncertainty. It doesn't say that we, in some sense, actually know what the discount rate is, but you're going to act as if the discount rate is 2%. That's going to be mathematically the solution to the Minimax-Regret policy. And what's going to happen when you do that, when you trace out, and we do our policy work looking out a range of several hundred years, it's going to keep maximum future temperature below 2 degrees centigrade for most of the parameter values that we use to weight cost and damages. It's not going to get it down to 1.5 degrees, which is what people talk about these days, but it is going to keep it below 2 degrees centigrade. Okay, that's the introduction. Now let me go to the next, and I've got this in different levels of broad introduction, now still verbal, but to get more into what's going on in the modeling, and then some math, and we'll see how far I can get. First, on the climate modeling. If you, I presume most of the people listening on the webinar are economists, but if you look at the climate scientists, the climate models are all based fundamentally on a set of deterministic nonlinear partial differential equations that describe large-scale atmospheric dynamics. Now, even though the physicists agree on the large-scale atmospheric dynamics, there's a lot of stuff that is uncertain about, that's led to lack of consensus about the right climate model. Because there first is numerous practical choices involved that are computation, discretization to solve these models, what solution methods you're going to use, and so on. And these things actually matter. They can lead to different forecasts. And then there are some parts of the physics that are still not completely understood. None of us are the physicists, but our understanding that literature is that particularly issues of cloud formation and heat transfer between land surfaces and the atmosphere are still not fully understood, and they must be approximated. And that's why there have been multiple climate models that have been developed. Each of these is a massive exercise. We did a fair amount of computation to what we're doing, but the physicists get on a supercomputer and let the thing run for months, it seems. And this is really big science work. But there are multiple climate models, and each reflects different but credible choices in model design and implementation. Now, what happens if you look across, we're going to look at particularly 6 models. They actually give different forecasts of the of the function that relates emissions to future temperature, and they're not trivially different, but substantially different projections of the amount of temperature change that we're going to experience. We're just going to say, well, there's if there's 6 models with 6 projections, that's what we know. The standard, the convention in the physical science literature has been to try to get rid of this deep uncertainty by combining the model outputs into single projections And they do that by averaging, even though there are persistent methodological problems in combining model projections. Now, the very simplest thing to do is to take a simple average. The physicists even have a name for it. It's a kind of cute name. They call it model democracy. But often instead of a simple average, they do a weighted average. And if they do have a Bayesian orientation, you may be familiar with Bayesian model averaging, where you take weighted averages based on subjective probabilities of which model is correct. So that would fall inside this domain. Well, they do it, and they have historical data that gets them and some Bayesian thinking, perhaps, that gives them some weights, but there's no consensus on this. And we have at the bottom here, this is a quote from a recent IPCC report. It states, despite some progress, no universal robust method for weighting a multi-model project ensemble is available. Now, that's all I'm going to say about it. Our PNAS article talks about that kind of uncertainty in much greater depth, but that's all I'm going to say about it here. What I want to focus on is the uncertainty regarding the discount rate. So I think, you know, we're all economists. If you're all interested in climate change, you must be familiar about the controversy about the discount rate. And it's a very interesting controversy, because it's not simply about a controversy about the empirical world, but it's a normative controversy about what discount rate should be used based on normative considerations. Now, to think about this, we have a section of our paper where we discuss this. You think about the famous Ramsey Formula. We don't actually use the Ramsey Formula in our technical work, but it provides a nice framework for conceptualizing it. So well, there are various versions of Ramsey, but we'll just take a simple version with the social welfare function that's additively separable in the utility of future generations. Rho is going to be the rate at which the planner discounts the utility of future generations. This is a normative parameter. It's, you know, how much do you care about future generations in a normative sense? And then we also have a question of, well, it's going to be a representative agent model. These things almost essentially always are. So utility is going to be a function of consumption. But then an ordinary utility function is not going to be enough. It's going to have to be a cardinal utility function. So we're going to have to care about curvature of how does the utility vary as consumption rises. And it's generally in the literature assumed to be a concave function. And for simplicity, people will often assume a constant utility elasticity function, and that's going to be minus eta. So that's going to be diminishing marginal utility of consumption. And then eta. Well, is eta an empirical parameter or a normative parameter? It's sort of in between. If you think of utility in a cardinal sense, then it's an empirical question of what is the curvature of the utility function. But if you think of utility only as an ordinal function, and then it's a question of what concave function to put in, then it's a normative parameter. And just as a side point, very early, I was a PhD student at MIT. I actually took public economics from Peter Diamond and actually Jim Murley's, who was visiting and at the time. And of course, Murley's famous work, and Murley's and Diamond, on optimal income taxation. This was a normative parameter there, because that led to redistribution in terms of income tax policy. So rho and eta are basically, rho is clearly a normative parameter. Eta is at least partially a normative parameter. What's purely empirical is G is the growth rate of consumption between today, which is time 0, say, and some future time t. The Ramsey formula says that delta, which would be the overall discount rate, is rho plus eta g, so that both normative and empirical considerations are going to combine. Okay, so you can see how both in that very simple equation play intrinsic roles. Now, in terms of uncertainties, the empirical value of G may be uncertain, and that's a question of long-run macroeconomic forecasting. Okay, it may be very tough, to forecast the growth rate of consumption in the future, but that is, in some sense, the simplest problem. It's like the physical science problem of forecasting the future empirically. The harder questions are rho and eta. And a planner may feel normative uncertainty about what value of rho and eta to use. And it's definitely going to matter in terms of what climate policy is going to be chosen. Now, this became, climate scientists or anyone who studies economic growth and long-run macro policy is very aware of this. This became a very public debate about 15 years ago between Bill Nordhaus and Nick Stern, because thinking in terms of the Ramsey formula, Nordhaus used 3% for the rho, for that intertemporal, how much you care about future generations. Stern used 0.001. And I'm seeing that Alan Stansted has come online as I'm talking, so he's going to be around for questions as well. Their policy implications were very, very different. Nick Stern concluded that policy should seek to reduce greenhouse gas emissions aggressively and rapidly. Nordhaus favored policies that act more modestly and slowly. And this was primarily because they use different values for this normative parameter rho. We do not want to take a position and say Stern was right and Nordhaus was right or somewhere somebody else is right. We argue against any attempt to cope with empirical and normative uncertainty by choosing a single discount rate. Instead, we study formation of climate policy, recognizing a set of possibly appropriate discount rates. Okay, I've done through the second level, and now I've got the third level here, and I have enough time to at least get into the basic math of this. And I think I've got enough time to do this. I know when I get to the detailed computation, I'm not going to get to that, but let's see what we can do. First, set up the ordinary optimal control problem where there is no uncertainty. So capital B of T is going to be baseline emissions. This is, there's stuff going on in the background, even without a formal public policy on emissions. There is abatement that's going on, and emissions from fossil fuel usage and so on that's going on. So this is, there's going to be some baseline emissions without an active public policy. And then A is going to be the actual abatement actions that the social planner undertakes. And this is posed, this is idealization that we as economists become comfortable with, of thinking of a worldwide social planner, and which of course is not true as a political matter, but still that's what's used in the literature. And the abatement is measured in the same units as emissions. And then there's going to be a cost for those actions. Okay, and the cost, that's the cost of the abatement, C of AT. What is net emissions? That's E of AT. That's just the difference between the baseline. You have baseline emissions, you subtract out the abatement, and you get the net emissions into the atmosphere. And so we can talk about paths. If you think about this over time, as paths or trajectories. And there's going to be a set of feasible abatement paths leading to a set of feasible paths or trajectories for net emissions. Now, let's talk about the emissions. The emissions become inputs to a climate model. This is where the physical science comes in. And then the physical science model is going to forecast global mean temperature. So if you go down here, you'll have a temperature, if you can see my hand on the slide. Temperature depends on what model you're using, and then it depends on net emissions. Okay, so these two variables at any point in time, temperature depends on what net emissions have been. This is cumulative net emissions, not at a point in time, but just accumulating overall past emissions, and what the model, the climate model is, and that's going to give you global mean temperature at time t. Now, then we take that global mean temperature, and that's going to determine damages. So that's the economic damages as of that time. Well, what's the overall cost? The overall cost is at the bottom. You have the damages, this is the economic damages from global warming. And then you have the cost of abatement, and the total cost of an abatement policy as of time t is the cost of abatement plus the economic damages. And this is where the basic trade-off comes in, is that if you abate more, it's going to cost more, but the temperature change is going to be less. That's embedded in here, is because the more you abate, the lower the temperature is going to be. And so you have this basic trade-off in abatement, that abating more costs more, but leads to less global warming. And that's right here. What does the planner want to do? Well, so everyone's going to be familiar with this, is that you're going to minimize the present value of this overall cost over a planning horizon. The standard of the literature has been to assume an infinite horizon. I have to say that Alan and Steve are not entirely happy with that. And this paper that we've just finished, which is now in our R&R status at one of the major environmental economics journals, it's it's our second paper, but we think not the last. One of the things we want to get away from is the infinite horizon setup and do this with a finite horizon setup. I don't have any time to talk about that now. With the infinite horizon setup, here's your minimization problem, which will look pretty standard to you. And you want to solve that. And, with some regularity conditions, there's going to be a solution to this. Okay, so that's going to be a standard optimal control problem. Now, Minimax-Regret. I got a couple of slides to do that. But here I got to go more slowly because this will be new. And then you'll see the guts of what we're doing. Is that now we don't know what the correct climate model is. So we have a set of climate models. There's going to be 6 of them for what we do in the computationally. And then we also don't know what discount rate to use. So that's delta. So it's going to be they're going to go from 1% to 7%. Well, if you did know the correct model and the correct discount rate, you would just solve the optimal control problem. If you do that, you would just solve this right here. This is just the optimal control problem where you use a particular climate model, MJ, and you use a particular discount rate, delta J, and that's all you do, nothing to it. And here's your associated minimum cost, plugging in the optimal abatement policy right over here. So that would be the standard optimal control problem. Now, the issue, of course, is that you don't know what climate model or discount rate to use. Let's suppose that you were to choose some particular abatement trajectory, AT. Then we have regret. I said before that regret is the degree of suboptimality. That's right over here. This in a particular state of nature. If delta I is the right discount rate to use and MJ is the right climate model to use, then this is the minimum of social cost. If you pick some suboptimal abatement policy, then under this model and discount rate, this is the social cost that the world will suffer. This mathematically, logically has to be greater than or equal to this. You would be just lucky if you were optimizing. Generally, this will be larger than this. And so the difference between this and this is how suboptimal you are, and that is called regret in the literature. Now, obviously, regret's bad. You don't want to be suboptimal. What you would like to do is to minimize regret. But to minimize regret, you would have to know the correct climate model and the correct discount rate. So you can't do that. You cannot minimize this function. What you can do is to say, well, look, I don't know what the correct model is, M, and the correct discount rate, delta I is, but I have a set of possible ones, which I gave before. Those were the capital deltas and the capital N's. So I can say, well, if I choose this abatement path AT, I can calculate maximum regret, which is right here. Maximum regret, flush it out, is just this thing in brackets is just before, but it's the maximum of this across all of the feasible deltas and M's. If for any of you have a decision theory background, this is second nature of maximizing across the set of possible states of nature. Well, so then what's a good policy? A good policy is one that minimizes maximum regret. So you take maximum regret over here, and then you take the policy, and then you minimize that over here. This is a saddle point problem. This is what makes the math not so trivial. And you solve this problem, and that's what we do in the paper. Okay, that is, I'm going to sit on that for just 1 second, because that's as far as I need to go on the math. I have a couple of more slides to flesh this out, and then I'm going to just skim through very briefly the exact computational work and then conclude. So this is the problem we want to solve for a particular specification of this problem. Now, if you're not familiar with Minimax-Regret, you may be familiar with Minimax, which embodies the principle of preparing for the worst case. And Minimax is doing a worst case analysis. I didn't put the math up, but you just look at under any given policy, what's the worst that could happen to me, what happened to the world, and then pick a policy that does the least bad thing for the world. In the EU, Minimax is somewhat enshrined in the precautionary principle for climate policy. That's not done mathematically, but verbally, it's basically a Minimax idea. Stephen Allen and I have argued strongly, and I've argued in many contexts, in other policy contexts as well, that Minimax-Regret is in some sense, a more reasonable policy criterion than Minimax. Minimax-Regret analysis uses information in a more nuanced and less conservative way than Minimax. Minimax-Regret is not ambiguity averse, which is a term you may know from behavioral economics literature. What regret measures is the potential suboptimality of policies, and choosing a policy to minimize maximum regret means choosing one to minimize the maximum degree of suboptimality across the policies under consideration. Now, I've having worked on Minimax-Regret policies now for about 15, 20 years, and given many seminars on this, I'm very aware that the first time you see this, it takes a while to sink in. And the sinking in partly is conceptual, and you can do it in your head, and it partly means staring at the math. But given the constraint on time, I'm just going to leave it at that now, and maybe in the discussion time we can come back to it. The final thing I want to say, and then I will just conclude, then run through things quickly and conclude, is on the use of delta, the set of possible discount rates, to express both empirical and normative uncertainty. Typically in decision theory, uncertainty means empirical uncertainty, uncertainty about a true state of nature in the world. Where our paper really conceptually goes out, I'd have to say we really go out of the mainstream about this. And Alan and Steve and I spent a lot of time discussing this. I don't know if there are other precedents for it, not just in climate policy or anywhere else for that matter, but we've become comfortable with it, is to think about a set of discount rates as expressing normative uncertainty as well as empirical uncertainty. Now, why may there be normative uncertainty? Well, if you're thinking about a utilitarian social planner, then the planner is supposed to represent the population. But it's not actually so easy if you think about ordinary human beings or even us professionals to be really clear about what do we want for our time preferences, what is our concern for intergenerational inequalities and so on. So there really may be uncertainty about what society, if you will, really wants. We go even further than that. We use the set of possible discount rates to express normative disagreements. To take, let's say, Bill Nordhaus and Nick Stern and say, look, they disagreed on what value of rho to use. And you can't say one of them is right, one of them is wrong. It's just they're different normative conceptualizations of that parameter. So what we're going to do is to use a framework that embeds both of them. And there is a different way to do this. And I say at the bottom that instead of the way we do it, you could just abandon the whole idea of a utilitarian social planner and set up the whole problem of climate policy as a non-cooperative political game. That if there are differences in what people think about the discount rate and the normative differences, then it's a non-cooperative political game. We're not against that. We think that's a kind of interesting thing, and it may be far more practical than the social planner setup, but that's really rough, and so that's probably for someone else to do rather than us. So we go this route, and we use the delta to embrace normative uncertainty, and what we say, and you have to think about it because it took us a while to think about whether this is a sensible idea or not, is that if you have a heterogeneous population that disagrees on what discount rate should be considered the true discount rate in some sense, also the model, but the discount rate is the main thing, then the use of the MMR rule to choose policy minimizes the maximum degree of suboptimality that will be experienced across the population. We have a discussion in this, a verbal discussion relating that to Rawls's ideas. This is not the same as Rawls, who actually did Maximin and more, but there's a bit of a, in a very broad sense, there's some similarity in flavor. You can look at our paper, which is available online if you want to get into that. Now, I think I'm doing okay with time. We're just about out of time. I'm just going to run through here. We have a computational model that we have to express the climate dynamics. We do that in a fairly simple way using the work of Matthews et al., who's a climate scientist. The main thing here is that you have what's called the carbon climate response function that makes the change in global mean temperature a linear function of cumulative emissions. And it's cumulative, not time-dependent emissions, is because these greenhouse gas, the carbon dioxide in particular, stays in the atmosphere a long, long time, hundreds or even up to 1,000 years. So it's cumulative emissions, and then climate, then the temperature is a linear function of cumulative emissions. Each model then, if I go over here, this temperature is a function of emissions, and each model then gives you a sensitivity of temperature to emissions. So that's where the 6 different models show up. Here are the particular models we use. These are 6 climate science models. You can read about them. We discussed them in greater length in the PNAS paper. For the climate, for the final thing, for the abatement cost and climate demand functions, they're simple quadratic functions. They're not our own. We take them from the literature. The cost of abatement as a function of abatement is a quadratic function with a parameter alpha. We take that from a paper by Dietz and Venmans in 2019. The damage function, damage is a quadratic function of temperature. We take that from Nordhaus and Moffat in 2017. Okay, then we go on, we solve it, we get results. I wish I had time to go through them. I knew I wouldn't. Just here, and we get a bottom line that Minimax-Regret, you're going to act as if the discount rate is 2%, and that's going to keep temperature below 2 degrees Celsius. Okay, to finish, just a couple more slides. Going back to the broad issues, we think that the Minimax-Regret rule provides a reasonable way to form climate policy with both empirical uncertainty about the climate and normative uncertainty, as well as empirical uncertainty regarding the discount rate. Our computational analysis offers a new reason for using a low discount rate. It's not saying that a low discount rate and that Nick Stern is right and Bill Nordhaus was wrong. It's rather that if you go through the Minimax-Regret analysis, you act as if it's 2%, because in a broad sense, regrets about making a mistake are larger and the discount rate is low, because you care about the future more. And so the cost to society of making a mistake is larger when the discount rate is low. I wish I could just say that. You might think that would just drive the discount rate down to our lower boundary of 1%. It turns out it does not. We can discuss this if there's time, because the model is a fairly complex model and drives it to 2%, not 1%. Well, and then we have some discussion here about using it for disagreement. I've already said that. And okay, last slide. Where are we now? We have results. We can do more calculations like this because our model is fairly simple and computationally tractable. Steve, who did almost all the computational work, may argue that it's not that tractable. I don't know how many days and nights he was up dealing with this and how much he learned about the intricacies of solving things using Mathematica. Maybe he can talk about that. But we could get far more complicated because we abstracted from various levels of different types of uncertainty. We don't know what's the right baseline emissions path to use. The abatement cost and climate damage functions are also uncertainty. We would like to encompass those as well. We did that by some sensitivity analysis that I didn't have any time to go into, but that's not the same as really encompassing them as deep uncertainty. Looking forward, we think it would be desirable to expand the analysis by embracing all of these other kinds of uncertainty as well. Okay, that's where we are. And I think we did it pretty well to I see from Carlos Madera. Yes, Carlos was a student at Northwestern some time back. So I think, Anastasia, I'll turn it back over to you now.
Thank you very much, Jack. It was a very, very interesting presentation. And indeed, we have a question by Rick van der Ploeg, where he says that Gilboa and Schmeidler give a nice axiomatic underpinning of minimax and their notion of ambiguity aversion. Is there a similar underpinning for Minimax-Regret?
It's well, like, how many hours do you want to give me to talk about the controversies in decision theory? There are short, well, let me give it. First of all, we do not do axiomatic decision theory at all. That's not the, I have nothing particularly against the axiomatic decision theory, but I am not the type of person who thinks that you need to axiomatize something to do it. Gilboa and Schmeidler, his work became very famous among axiomatic decision theorists in the 80s and on to the present for axiomatizing minimax or max and min. I have to say that for macro work, those of you familiar with Lars Hansen and Tom Sargent's work on robust macro policy, they care a lot about that axiomatization. And so they go that way. There have been, on Minimax-Regret, there are axiomatizations. We don't even reference them because it's not our of importance for the work, from the way that we come at this conceptually. This has been, I'll say this has been controversial since the early 1950s. Hermann Chernoff in Econometrica in '54 argued against Minimax-Regret because it violates one of Savage's axioms, particularly the independence of irrelevant alternatives axiom. And Savage viewed, I have to say he normatively viewed it as this was a sine qua non, that that violating that axiom makes Minimax-Regret unsuitable. This has been argued among decision theorists for about 70 years. And I do not think there's a consensus view on it now. I wrote my own paper, as I say, I can't go on for hours. I wrote a paper in a decision theory journal called Theory and Decision, called Actualist Rationality, back in 2011, and I argued strongly against that. And I think Minimax-Regret is perfectly suitable. So however, that, happy to go on much longer about that, but it would take us off to the decision theoretic aspects of it. So I'll hold myself from going further on that right now.
So let's go to Carlos Madera's question, and one housekeeping issue. Yes, there is no Q&A box, so please post your questions on the chat function.
Rick Ploeg says he likes.
Yes.
Well, good for you.
Okay, so Carlos is saying that he's working on a related empirical model. So suppose one collects the GDP losses implied by climate change from 6 major reduced form articles. He puts the formula there, which is equal, y is equal to beta multiplied by x. Obviously, these 6 studies disagree among themselves for a wide range of countries. 3 of the 6 studies have positive correlation for their GDP losses. The other 3 even show negative correlation. How can one represent the GDP losses for the 100 countries and summarize their uncertainty?
Oh, so he's going down to the country level and then aggregating up. Of course, well, in conceptually, it's no problem. In practice, of course, it'll be a big computational problem. And I'll give a short answer, then maybe Stephen Allen can add. We, of course, work at the global level, which I think has been the norm. You could take this whole modeling enterprise and work it down to disaggregate by country or region or whatever you want, and then express uncertainty at that more disaggregated level, and then aggregate back up to the world level. From that more detailed. So of course, that's going to give you a more complex model. Conceptually, it would be the same as what we're doing, but it would be far more complex to do that disaggregation. Steve or Alan, do you have anything on that? Does anyone do that, Steve or Alan, to disaggregate?
let me back up a step. Let me say something about the initial question, Mr. Proctor, I believe, about empirical evidence that there's always negative macroeconomic effects. The question would be, what would constitute empirical evidence? Because there's necessarily a counterfactual, right? You have two cases where you have an economy in one reality, you run, it's the baseline, the other reality you include climate policy. So after the post hoc, that requires modeling of some kind. So it's very hard to see what a purely empirical evidence one way or the other would be. There's a long history, very briefly, about so-called negative cost abatement possibilities, particularly around energy efficiency. To the extent that those are available, I tend to think they're extremely small. On the scale that we're talking about here, the idea that would, my own view is that the idea would be would actually be purely stimulative is implausible. It's also a matter of what constitutes macroeconomic. Is it employment? Is it output, and so forth? So I'm not sure what Mr. Madera means by exactly what the analysis was that he's referring to, and what a correlation would be. But yeah, that's what I would have to say. Oh, can I also say one other thing? I want to acknowledge Professor Vanderploeg, who has done work in a precursor to some of our work, is a work he did several years ago. Very nice study on Minimax-Regret in this context, comparing Minimax-Regret and Min-Max. So shout out to him.
At the international level, the global level that we're considering, if you try to break it down, there's really the political problem of coordinating policies across different countries. And that's a wholly different problem, one that we don't address at all. It can be formulated as a game theoretic problem. It's not easy.
We have one more question. Is there empirical evidence that abatement always has negative microeconomic effects?
That's what I was just referring to.
So I have one question that I would like to ask, and that's, how would advances in green technology, which end up lowering abatement costs, be part of this model? What, if you could explain, what would the effect be?
I'm going to turn that to my colleagues. I should tell you, for those of you who know, I'm mainly an econometrician by background. Alan's an energy policy analyst at Lawrence Berkeley Labs by background. Steve does environmental economics and computational economics. So they're both closer to this than I am.
So let me make sure I understand your question, Anastasia. You saying what would be the consequence of including technological change in that green technological change in the model, or by way of the background, how does it inform what we've already done, or both?
Both.
Okay, so several parts of the answer. First of all, the baseline in a model like this always incorporates some degree of technological progress. There's the phrase baseline or business as usual is sometimes used. The idea is that, in some platonic realm where you have no policy, let's compare policy with that. Of course, there's already policy. Baseline, even if there's not policy, there's technological change of various kinds, which tend to be decarbonizing, even if they're not the consequence of some kind of global policy regime. So the baseline already incorporates some degree of what's called decarbonization. Bill Nordhaus has had this in the DICE model for a long time. There's just empirically, if you look over time, there's a declining ratio of carbon emissions to output. So that's there. Including it explicitly in our model. So, but it's not, so our model is autonomous, it's not autonomous in the sense we don't have any form of technological change in the objective or damage functions for that matter. That's something to do. Very interesting. Putting some kind of technological change. It's a matter, that's a whole world unto itself. The standard in these kinds of models is autonomous or exogenous, where it's just a time trend, right? You're sort of agnostic about where it comes from. I tend to think that would change the results, but not qualitatively. It would change. If you have decarbonizing technological change for free, obviously that's going to lower the costs. It's going to lower the Minimax-Regret and so forth. What would be interesting is, so you also have declining costs of declining damage impacts because of increased adaptation policies. So I'm thinking out loud here, but it would be very interesting to include those side by side. You see, okay, what is the relative contribution? Getting into more sophisticated forms of technological change, what's been called endogenous technological change in the literature, where the green technological change is part of economic decision making in the model, responds to incentives and so forth. That's a lot harder, and it would be extremely interesting. There's not a standard way of doing that, and it hasn't, to make a long story short, taken root in main integrated assessment models a great deal. So that I would be a little bit more cautious about saying anything about.
I'd like to add one thing. There's no doubt that there are some emissions reduction technologies that can be done at a profit, so that there's no cost to them or that there's negative cost associated with them. But when we're talking about the level of reductions that have to be achieved in order to stabilize the temperature, keep it below 2 degrees and so on, that's just too big for the zero cost efficiency gains to be operative. It just can't be done. And we think that it's sort of a political dodge that politicians like to make it seem as though all these green things can be accomplished at no cost to society whatsoever. We don't believe that that's the case.
Thank you. Glenn Rudebush has a question. How should the public choice of adaptation, which alters the damage function, enter your analysis? He continues, abatement and adaptation are a joint public choice. And how does the social cost of carbon fit in the analysis?
I said at the very last slide that there's many directions for future work to expand what we're doing, and taking adaptation seriously as part of this, jointly with abatement is certainly one of them. So we're not in a position now to know how far we can go with this. I might mention, I'm going to give a plug because his book is still not out, but Bob Pindyke has this new book, which we've all seen, and I don't think it's been released yet, but some of you may have seen it. It's been floating around, where he pushes very hard on adaptation, thinking that abatement just can't do it on its own. So we would certainly like to go in that direction of adding abatement, adding adaptation in, but we haven't done it yet. And the final thing, social cost of carbon, say to Steve and Alan, we have managed to avoid it in all of our modeling. It must be buried somewhere in there. We haven't had to come up with the social cost of carbon in any of the work that we've done. We haven't, can we back it out of our, what do you think, either of you? It's interesting that we haven't needed it.
Well, depends on how you define the social cost of carbon. That seems like a kind of a dodge, but there's some variation in this. The definition I think Nordhaus uses, it's the marginal long-range marginal damages, marginal damage from a unit of emissions, right? So in that sense, our damage function contributes to that. What you'd have if you what the model takes into account, of course, is at any time, if the damage function, it's the instantaneous reduction in output plus the long-term reduction of output. And so we could back that out. I haven't thought about exactly how to do it, but it's embedded in the results.
Yeah, it must be embedded.
It's embedded. The social cost of carbon is a sort of a shorthand way of evaluating micro projects, whereas this is a global optimal control problem. Social cost of carbon is built in a way that's not sort of the shorthand that's used for policy.
The one thing I'm going to add to this, because again, we could go on for hours. I had quite a long conversation with Michael Greenstone about this. And of course, I care about uncertainty all the time. And I was saying, how the hell do you come up with a single number for the social cost of carbon? And he says, well, we have to, because the Office of Management and Budget in the United States requires it. And so there has to be a number. And so how do you do that? And I never feel comfortable doing that. So I don't think any of the three of us would want to, if someone said to you, you're working for the government and you have to come up with one number for regulatory purposes, what number would you use? I don't think any of us would want to stick our necks out and do it that way. But somehow that the concept of the social as cost of carbon, as Alan was saying, is got to be embedded in what we're doing. But it's interesting question for how we might.
Yeah, let me just, it just occurs to me. In some, our model sort of, I didn't think about it this way before, but our model actually embodies deep uncertainty about the social cost of carbon in a way that, is that true? No, I take it back. That's not true.
Not the damage function. Just
not the damage function. So I'm not sure what Professor Van der Vloed means about the extra term added to the mark. Social cost, the damage function, right?
Well, good thing about giving a seminar is that we get new things to think about too.
Well, I don't know if Rick or Glenn would like to unmute themselves and continue the conversation. We're 8 minutes. Yeah, well, I guess Rick is unmuted.
He's unmuted, just don't have a visual, but.
And Glenn, perfect.
Hello, can you hear me now?
Yes.
Yeah.
Yes.
Okay, great paper.
Thank you.
I think some of you define this extended cost. So the cost of march, the cost of abatement, and then you add this extra term.
Yes.
And I think that can kind of correspond to some risk adjusted or Minimax-Regret adjusted social cost of carbon. And then that's probably what you want to price. So I think it comes out very easily out of your framework. So it's rather neat. Yeah. Very nice. Huh.
Thank you.
I had little other question about, this other stuff by Marty Weitzman and Christian Gollier. They say, well, we don't know the discount rate, but we don't know the growth rate. From the Keynes-Ramsey rule, then the discount rate is uncertain. So let's take the certainty equivalent value of the discount rate. And then they show that the certainty equivalent value of the discount rate declines over time. So that the risk adjusted, if you want, or the certainty equivalent value of the discount rate is not a constant, but it declines over time. So very far in the future, you use a much lower discount rate than closer today. So I wonder whether something like that may be somewhere in your stuff as well. But anyway, that's something in my previous work I worried about, and we shoved it under the carpet. But it's something we need to think about.
We're certainly aware that some of the literature has a time varying discount rate, and particularly the discount rate dropping over time. The reason we stayed away from it for practical computational reasons. I think instead of having 7 different discount rates, we'd have a stochastic process we'd have a whole process for the discount rate. And my God, the deep uncertainty there where you don't know that entire process would be just well beyond what we thought we could do. But conceptually, I think we agree with you that thinking about the discount rate as possibly a time varying parameter and having a deep uncertainty about that is perfectly sensible. Steve, do you have anything you thought about that regarding the Ramsey modeling, right?
Yeah, the problem is that the curse of dimensionality makes itself shown very, very quickly.
Sure.
calculating the regrets. It goes from calculating 36 regrets when there's just uncertainty about the climate model to over 1,700 when there is uncertainty about both the discount rate and the climate model. So that you multiply the two things and then square that, it gets huge very quickly. And one of the things we're trying to think about is whether there's a way of speeding up the computation or cutting it down somehow to make it more tractable. We don't have supercomputer.
Another thing is, in a sense, you'd expect that there is kind of statistical uncertainty and modeling uncertainty. So imagine you get these Richard Toll Nordhaus style damage functions. They are highly uncertain. They're almost Cloud Cuckoo Land damage function, you could argue. And then you have this whole climate impact lab of Michael Greenson, particularly Solomon Xiang, and they get very different estimates. But they get underestimates, they get also statistical distribution. So any idea you have model uncertainty, is it Solomon Xiang? I'd give him a 90% prior and maybe 10% prior to the damage function everybody else uses. But then you have modeling uncertainty and statistical uncertainty. And I think that's the next step forward, I suppose.
Well, modeling uncertainty I didn't use the word when I gave the talk. Model uncertainty is another one of the synonyms for deep uncertainty or ambiguity. We do have alpha and beta as the parameters and the damage function and abatement cost function. And we certainly know how to add that in to make deep uncertainty about the value of alpha and beta, keeping the quadratic form. And that's one of the things that we do want to do. And that may be computationally feasible. So that could be not too much in the distant future in our program of work. We certainly agree that's important.
Right.
Len?
Yeah, just to come back to the social cost of carbon, I mean, that is crucial. Just to second Michael Greenstone, that is a crucial concept in U.S. climate policy, since a lot of it is being done through the regulatory system. So I don't think just saying it can't be calculated is a good solution. That says, oh, we should disregard the cost of climate. I think the U.S. courts have said it's certainly not zero, so it's something we should try to figure out and then take into account. One other thought is, another question was, you take a range for the discount rate between 1 and 7. 7 seems really high in a world where interest rates are close to zero and real interest rates are close to zero and even negative. But I take it wouldn't matter if your range was 1 to 5 or 1 to 4, because it's really the 1. It's really the lower bound, given the nonlinearity of the exponential nature of discounting. It's really the lower end that's driving the results.
That's correct. If we had done 1 to 5, we would still get the same result.
Okay, that's good to know, because 7 seems.
Yeah.
We've done some tests with breaking up the range from 0 to 1, and it comes the MMR solution comes out to be somewhere in that range. So that's just reinforcing what Chuck said.
Go back to the real world, the real world of American regulatory policy, which I usually stay away from as an academic, but occasionally I see it. There was a National Academy, I got dragged into this. There was a National Academy of Sciences study on updating the social cost of carbon not too long ago. I got dragged in it as a member of the National Academy. I got assigned a job as the monitor for that study. And there got to be a huge controversy. It was a good study. It was a very good study. But in the review process, there was a lot of controversy about handling of uncertainty. And one of the things that happened, and some of the reviewers who, of course, they were I wasn't anonymous, but the reviewers were. Someone will give names and saying, look, you're just ignoring uncertainty. The pushback we got is we have to ignore uncertainty because OMB says we have to come up with a number. And this is the real world and we've got to do it. And well, that argument won in the end. The report went out and it actually said, we've got to do this for regulatory purposes. This is not for science. I found that as someone who, tries to bridge between the scientific study of policymaking and the real world study, I find that curious. I can't be just an armchair academic and say that what OMB says doesn't matter. It does matter, but it does leave open this weird question of what do you do when the regulatory apparatus goes down a certain channel and says these are the concepts they're going to use, but when you know scientifically that's not what you should be doing. So I don't have an answer to you, Glenn, but it's I see a tension there.
I want to add something to this. Of course, it's an extremely important point. It's kind of foundational, if you will. One of the things we've said in our, I don't know if we've said in this paper, but certainly in the PNS paper, our first paper last year, has to do with the characterization of uncertainty having to do with climate. The IPCC, as you probably know, has devoted enormous effort to uncertainty quantification. They have their own system to do it. And in the climate modeling community, there's been, for decades, there's been aims at sort of the addressing uncertainty by trying to combine the model results, right? There's the model uncertainty, different results across the climate models, combining them into single answers. So they all give different trajectories for a given policy or whatever. So you average them in some kind. And so there's this whole literature on how you do that and how hard it is to do that. Part of the reason that the climate scientists have done that seems to be that they think that's what policymakers want, right? The policymakers want a number. So you can't give them a whole bunch of numbers. You got to give them one number. And, not without reason do they think that. But one of the points we make is that one of the attractions of Minimax-Regret is that it allows you to, it gives you a way of making a single decision given the uncertainty. In other words, if policymakers, they want to know what to do, right? That it comes down to what decisions should we make. It's sort of what NMR allows for is to answer that question unambiguously without having to boil down the uncertainty into a point estimate, or sort of artificially. And I think that's one of the most attractive things about it, is that it bridges that gap between uncertainty without between uncertainty decision-making in this realm without artificially suppressing the uncertainty.
We also think that there's a consensus building element to the way we do it. We don't say that everybody has to agree on what these normative parameters are. Rather, the MMR gives a way of coming to a conclusion without suppressing the disagreement that may exist among the population.
So we're 18 minutes, but if it's okay with you, I'm happy to continue with the questions.
Sure, this is fun.
Can I go back to Mr. Proctor's question about what does our paper imply for the 1.5 degree goal? So when we started doing this work several years ago, in the initial formulation of the model, we went back and forth about, okay, should we set it up in terms of these climate targets, which are, become sort of the coin of the realm in international negotiations and the way people conceive about it. You can't really do that in this context, because without introducing implicitly in the idea of a climate targets from an economic point of view is that if you exceed the target, you have unacceptable costs or something. But it's not the language of climate emergency and climate crisis and and the idea that we're all going to fall off a cliff in 10 years if we exceed the 1.5 degree target is kind of how the discourse goes. Of course, it's not true exactly, but you can't do this kind of analysis without actually putting including an explicit cost of exceeding it. And so that's sort of where we end up in this cost benefit world. I can't remember what Steve calculated this, of course, what maximum temperatures end up being in these calculations. But I think going forward, something we've talked about, which is so the world is manifestly not going to meet the 1.5 target. I mean, that's kind of a given. And now, so the action is between, whatever we can do is better than not doing anything. So let's talk about 3 degrees. But actually, the uncertainty between 1.5 and 3 degrees, exploring that is something that we've talked about. In other words, Minimax-Regret to approach to the, I'm not going to be able to articulate this right now. Anyway, it's a really interesting question about sort of the trade-off between going from 1.5 to 3 degrees with respect to the cost of abatement versus damages, and how Minimax-Regret analysis would say about that thing specifically. So that's a really interesting question.
One last question from Carlos Medea. To defend a bit the policymakers, they sort of get complicated with intervals, but they do care about robustness and cross different authors, meaning they enjoy reading that different models and different authors coincide or disagree. Well, that's a comment.
Well, Carlos took econometrics from me, where he saw lots of intervals in which I tried to persuade the PhD students that they should become comfortable with intervals. And I'll say, if this is the last question, in addition to doing scientific work on policy making under uncertainty, I've become involved with the question of communicating uncertainty, and the question of what policymakers or ordinary human beings can handle is become okay, Carlos. I'm not going to. Is pretty important, and I don't think that. I'll just say quickly, I don't think this is. There's a quick, simple answer to that. Even in today's world, there are some policymakers, there are some ordinary people, there are some science journalists who are quite comfortable with uncertainty, even deep uncertainty, not just probabilistic, and want to see it, and actually don't trust numbers because they think, how could you possibly be so certain? On the other hand, there are people on the other side who just want to see a number, as Alan was saying before, and you got to deal with them. I see this over the long run as a kind of cultural issue, an educational issue, and this is particularly bad in the United States, worse than in the EU or in the UK. The Americans in particular don't seem to have a stomach for uncertainty. I spend a lot of time in London, and I found that Brits and British policymakers are much more willing, including people at the Bank of England, where I spent a little bit of time. They think about uncertainty, including deep uncertainty. So I think these things are correctable in some sense. Just to put some optimism on it. At least that's the way we're going.
Let me add an anecdote to this. Over the years, working in energy policy, specifically energy modeling, I've been in some very interesting conversations in Washington. I remember one where energy modelers were talking to staffers in Congress, and the staffers, they're very smart, these people. There's a reason that they're working for Congress, and a lot of them have science backgrounds, and some of them have PhDs. And so they're being given modeling results, not integrated. This is a different modeling context, but giving modeling results where, okay, here's the answer. And they say, okay, well, where are the error bars? Right? Where's the uncertainty? I mean, and an obvious question, right? And when in the energy modeling context, the models have long since got so complicated, you can't really say anything about uncertainty. I mean, it's a whole kind of modeling paradigm. The more detail, the better. Of course, there's a big problem of illusion of precision there. But I think there's a lot of, even among people who in the policy world who are not economists and not decision theorists, there's quite a bit of good intuition about things. These people are not stupid, and I think even if you don't give them formal uncertainty analysis, they understand there's a lot of ambiguity. It's uncomplicated and so forth. What they want to know is something about the lay of the landscape, right? I mean, they want to know, they are aware of different answers, different models, as the comments suggested, and they want to do the best they can. And so I think that I like to think that our work is kind of contributing toward that end. I mean, it does allow them to take into account a kind of uncertainty without, you know, like I said, artificially trying to make it go away or saying this is the only this is the model to choose.
I would like to thank you all. Thank you, Chuck. Thank you, Steve and Alan. This is the first time our webinar is lasting 1 hour and a half, but I guess the conversation was so interesting. So thank you very much.
Thank you. And thanks so much to all of you who are joining us today. I really appreciate your interest and your comments.
Yeah, thanks, everybody.
So I just wanted to add that our next webinar is on June 20th as we continue the series on modeling from frameworks. So until then, thanks again. Thank you all for joining.
Thank you.
Bye-bye.
Bye-bye.
Okay, bye. Bye all.